Hi, today we're going to work on improper integrals. And those are integrals that are just not very proper. So what do I mean by that? Well, look at this limit of integration. I want to do the integral from 1 to infinity of 1 over x squared dx. So that's what's making it improper. Now, the first thing I want you to do is let's remember what integrals represent. And in this case, let's think of it as area under a curve. So what does the graph 1 over x squared look like? Well, hopefully you don't have to grab your calculator and look at it. But it looks like that. And so we're talking about the area from 1 to infinity. So that is all of this forever and ever and ever and ever. And we know that it's getting closer and closer to the x-axis, but it never hits it. So it seems like this should be an infinite amount of area. So let's go ahead and do some calculations to see what we get for this problem. So before you can deal with integrals in the sense that we've done with antiderivatives, we have to deal with this infinity here. So what we're going to do is we're going to rewrite this and say what's the limit, and pick some variable, I don't know, I'll use a, as a approaches infinity of the integral from 1 to a. Because all the work we've done with integrals goes from one value to another, not to infinity. So 1 over x squared dx, or dx over x squared. And so now we won't focus on the limit until after we've worked out the integral. So this is going to be the limit as a approaches infinity. And what's the antiderivative of 1 over x squared? Remember, that's x to the negative second, so we add 1 to the exponent, makes it negative first. We have to offset the negative, so we get negative 1 over x. If you differentiate that, it's going to become positive 1 over x squared, so that works. And we're going from 1 to a. Okay, so now let's evaluate this using these limits of integration. So we have the limit as a goes to infinity of negative 1 over a minus a negative 1 over 1. So that's the limit as a goes to infinity of negative 1 over a plus 1. Alright, so now we can look at the limit. So as a goes to infinity, what happens with this expression? Well, the negative 1 over a, as a gets bigger and bigger and bigger, negative 1 over a is going to 0, and then 0 plus 1 is 1. So this is telling us that this area, which goes on forever and ever and ever, actually is going to equal 1. And that's kind of a tough concept to wrap your head around. But it's a finite area, even though that curve goes on forever and ever and ever. Alright, so let's take a look at another example. How about the integral from 1 to infinity of just 1 over x, not 1 over x squared? So, once again, I want you to get a visual. What's 1 over x look like? Put 1 there. Well, that's this curve. And then over here, in the third quadrant, but we're not concerned with that, we're going from 1 to infinity. Now, it seems like, well, that maybe it's the same answer. Although you have to remember, there's a big difference between 1 over x and 1 over x squared. For the 1 over x squared graph, our curve was approaching the x-axis much faster. So, for example, when x is 10, we have 1/10 versus 1 over 100. And when x equals, let's say, 20, this is 1 over 20, and this is 1 over 400. So it's approaching it a lot faster. So it seems like this area would make sense that this area we're looking at now should be more than what we had before. So let's see how much more. So first of all, we want to make this a proper integral. So we're going to take the limit as a goes to infinity of the integral from 1 to a of dx over x. So let's find that antiderivative and evaluate it at its limits of integration. And that's going to give us, what's the antiderivative of 1 over x? Oh, that's the natural log. Now it's the natural log of the absolute value of x, but because we're going from 1 to infinity, those are positive values, so I can just write the natural log of x, evaluated from 1 to a. So we're looking at the limit as a goes to infinity of the natural log of a minus the natural log of 1, but the natural log of 1 is 0. Alright, so now, as a goes to infinity, what happens to the natural log of a? And once again, this is a totally different graph, but I want you to visualize, what's the natural log look like? Well, it looks like this. It's increasing everywhere. And so as a goes to infinity, what's happening to this graph? Well, the y values just keep increasing and increasing and increasing. So this limit is actually infinity. And so that kind of really should blow your mind, because in the last example, that area wound up being 1, and here we have an infinite area. So like I talked about, the difference between the two graphs is the first graph was approaching the x-axis much faster than this current graph. And so this current graph is approaching the x-axis at such a rate that the area between it and the x-axis winds up being too large. So we would say that this diverges, or it's an infinite area. So that's kind of bizarre that we have such a big difference between those two problems. Let's look at another one. Oh, what happens if we want to do the integral from negative infinity to infinity of 1 over 1 plus x squared dx? Alright, so now we have two problems. Both our limits of integration are negative infinity and positive infinity, so we're going to have to fix both of those. So one way you could do it would be to split it up. And so, for example, we could do the integral from negative infinity to some constant, I don't know, 0 would make sense, of 1 over 1 plus x squared. And then plus, and then do the integral from that same constant, in this case I chose 0, to infinity of 1 over 1 plus x squared. Now with a little bit of insight, and maybe you, or hopefully you know what the graph looks like, but even if you didn't, we could go ahead and graph this quickly. And the 1 over the quantity 1 plus x squared, zoom 6, and then let's zoom in a little bit so you get a better picture. So if you notice the symmetry of this graph, so the way I split up my integral from negative infinity to 0 is actually going to be the same amount as from 0 to infinity. So I'm going to make my life a little easier, and I'm just going to say twice the integral from 0 to infinity of 1 over 1 plus x squared. And now I'm going to use a limit, so it's going to be 2 times the limit as a approaches infinity of the integral from 0 to a of this function. Now, what's the antiderivative of this function? Do you remember that one? Well, hopefully you realize that that's an arctan. So limit as a approaches infinity of the arctan evaluated from 0 to a. So that gives us 2 times the limit as a approaches infinity of the arctan of a minus the arctan of 0. What's the angle whose tangent equals 0? Well, that's 0. Alright. Now, we're looking at the limit as a goes to infinity of arctan of a. So you might not remember this too well. So let's look at the tangent. Remember, the tangent graph has asymptotes. And 2 of them are at negative pi over 2 and pi over 2. And so the tangent graph looks like this. So what does the arctan graph look like? Well, that's when we reflect that graph over the y equal x line. So now let me put pi over 2, negative pi over 2. And now we have what were vertical asymptotes are now horizontal asymptotes. And so it's going to look like this. So now that should make it really easy for you to evaluate this limit. What's the limit as a goes to infinity for this graph? Well, obviously it's approaching that horizontal asymptote of pi over 2. So we wind up getting 2 times pi over 2, which is pi. And how weird, how unusual, maybe it's just for me, that this area under the graph, let's kind of cheat a little bit here, let's say 7 from, I don't know, negative 2.25. I don't know how far that went. I should have gone a little farther, to positive 2.25. That this area, and of course it keeps going forever and ever and ever to the right and to the left, that total area equals pi. Kind of bizarre. Okay, let's look at another example. How about the integral from 0 to 1? This doesn't have infinity in it. So it seems like, well, this is just fine, let's evaluate this. But wait a minute. Remember that 1 over x squared graph from our first example. Now we're saying from 0 to 1. So let's copy this. And let's paste that. Okay, so now instead of this red area, now we're looking at a different area. Now we're looking from 0 to 1. So now we're looking at all this. And you can see that that graph keeps going up and up and up, closer and closer to the positive y-axis. So how much is that area? So remember when we did it the other way, from 1 to infinity, we got an area equal to 1. So let's see what happens in this case. So the problem here is my function's not defined at 0. So that's what makes this improper. So I need to change this to a limit. I could be creative if I like to keep things in the same order as I did before. So what I could do is switch my limits of integration and make it negative from 1 to 0 of 1 over x squared dx. Not that you have to, just to show you some tricks as you're working through problems if you get stuck and something will help you a little bit. So in this case, we're going to do so I'll put the negative integral from 1 to a. And now, by the way, we're approaching 0 from the right. So that's important. So I need to put that in my limit. So the limit as a is approaching 0 from the right. So positive values of 1 over x squared dx. Alright, so we need to figure out the limit as a approaches 0 from the right of the antiderivative of this. Remember, it was negative 1 over x, but we have a negative out in front, so it's a positive 1 over x. And that's evaluated from 1 to a. So that gives me the limit as a approaches 0 from the right of 1 over a minus 1. Now as a approaches 0 from the right, so we're getting smaller and smaller positive numbers. So what is 1 over a? What's happening? With 1 over a, as a gets smaller, like when a is 1/10, when a is equal to 1/10, then 1 over a is going to equal 10. And when a is equal to 1 over 100, then 1 over a is going to equal 100. So it's getting bigger and bigger and bigger positively. And then subtracting 1 isn't really going to do much. So as a gets smaller and smaller and smaller, this expression is approaching infinity. So that's really weird because this area over here is infinite, yet this area was equal to 1. So this concept of looking at values and limits, that's going to be really helpful if you understand this thoroughly when you start studying series. Let's look at one last example. Does the integral from 0 to infinity of cosine of x dx converge or diverge? Alright, so let's just tackle this like we have before. The issue here is infinity, so let me write this as the limit as a approaches infinity of the integral from 0 to a of cosine of x dx. So we take the antiderivative, which is sine of x, and we're going to evaluate that from 0 to a, and then we're going to take the limit of that expression as a approaches infinity. So we're going to figure out the limit as a approaches infinity of the sine of a minus the sine of 0, which is just 0. So what's the limit as a goes to infinity of sine of a? What is sine of a approaching as a gets bigger and bigger and bigger? Well, it's not approaching anything. It's oscillating between -1 and +1. So therefore, this integral from 0 to infinity of cosine of x diverges. Okay, so I'm splitting this up into 2 parts, so that's the end of part 1, and then you can go ahead and watch part 2.